Okay. First, let me share my screen. Can you see my screen?
Yes, Dr. Ali.
Yes, sir.
Yeah. Like Basics of Electric Power Network, that is the title. Just one thing, I think about 10-15 minutes ago, I just updated the slides. I have added several new slides in addition to what was available. Did anybody download or printed or?
Yeah, I had a look at it.
Oh, okay. But I uploaded the updated. So what you look, that is fine. But in addition to that, there are another 7 or 8 new slides I have that I am going to discuss here.
Okay.
That will help you a lot. But I already uploaded. Okay. So therefore, the goal of today is kind of the review of your past knowledge, especially the electric machines, which are the essential components of electric power network. And that knowledge will help you a lot to understand the subject matter of this course. Yeah, like you have to understand the working principle of each of those components. Plus the slides, new slides that I have added are about the three-phase circuits that you have to understand. So I'm going to go over. Therefore, I think it will help everybody, each of you. So please have a look. Uh, so what are the major components in power network? So you remember that in the last class, I was discussing with the power flow, how we get power from a power plant to our home, right? I was showing you there is generation portion, transmission portion, distribution portion, and finally your home. But in between, there are lots of components. Those are the major components in power network. So what are the components? Number one is synchronous generator. So keep in mind, this synchronous generator, which is actually located in the main power plant. Therefore, all over the world, everywhere, if you see that it is power plant, then that is the synchronous generator, not any other generator. Now that synchronous generator could be nuclear based, could be coal based, could be oil based, could be steam turbine, could be hydraulic based. So accordingly the power plant name goes like hydroelectric power plant, nuclear power plant, or a steam power plant. So according to the fuel input, but all are the synchronous generators. Just simply keep in mind. So all over the world, the same tradition. And then these days, I mean, these days been not just in recently, at least last 20 years, instead of conventional synchronous generator, permanent magnet synchronous generator is being used. This means if it is not permanently magnetized, then you have to excite it by providing external DC source. So we'll be discussing those things today. So keep in mind, for example, as a power engineer, if you are to ask to choose a generator which is, I mean, between these two, either synchronous and then permanent magnet synchronous, of course you will be choosing this one because there are some advantages. Therefore, simply take that for the new power plant, you must put the permanent magnet-based synchronous generator. And then the other essential component is transformer, which is often treated as the heart of the power network. Like that way, we have our live heart. The similarly, transformer is the heart of any power network. If the transformer goes out, then we will be under dark. And then there are lines. These lines mean basically these are the three-phase transmission line or three-phase distribution lines. And those lines have lots of resistance, inductance, and sometimes capacitance. And then there are various controllers like voltage regulator, transient stability improvement controller, other type of controller. And then various loads, basically the industrial load and residential load. And then again, the loads could be resistive, inductive, capacitive, or combination of any of those two or all of these three. And then in case of industrial load, mostly those are the two types, three-phase induction motor and then the three-phase synchronous motor. Therefore, for example, paper industry, sugar industry, jute mill industry, whatever the industry is, mostly induction motor and sometimes there are synchronous motor and all are the three-phase. So therefore, these are the major components. So today we'll be looking most of the major components, their characteristics, their dynamics and working principle, and that will help you a lot. Now moving forward, you see, this is the DC generator. So therefore, as I told you that although you all have studied this on, at least at the undergraduate level, or you might not have studied this on, but today it's a great chance for you to have a look. At least you will understand the working principle, how it works. So therefore, you see there are two parts. One is called armature rotating part, other is called the DC field, that is the stationary part. One is the rotating part, other is the stationary part. So at this point, just let's stop this one and let me go you to the whiteboard. So that will help you a lot. Okay, can you see the whiteboard, everybody?
Yes, Dr. Ali.
Okay, thank you.
Yes, Doctor.
You see this one and okay. So we are, simply discussing the DC generator. Okay, so this is DC. Okay, and there is North Pole and South Pole. Okay, and then this is the armature. So there are coils. So basically, just one set of coil, and then this is rotating at a certain speed. Okay, so therefore, everybody simply take in this way, to generate voltage, you need two things. One is the speed and other thing is a magnetic field. You must need two things. With the only one thing, you can't generate or develop voltage. Now, in case of DC generator, there are two parts. This is one part, which is called, this is called the armature. So this circular body on which the coils are mounted, on which the voltage will build up, it is called the armature. And then this one, you all know, this is the magnet. So in case of DC generator, and then here you need some sort of prime mover. Let me write down the term. Prime mover. So prime mover means who will make rotation. So now you can use your own hand. Okay, let's use my hand and then make it rotate. But it is not possible to make it rotate by your hand. So you will be tired at some point. That's why you must need some sort of turbine, which is like nuclear turbine or gas turbine or oil-based turbine. So those fuel input with the help of turbine will cause rotation, and this is called the shaft. Have you remembered? So this body is called the shaft. So once the shaft start moving, and because the coils are mounted there, so therefore you look these coils, because this thing is moving. So once it is going under the jurisdiction of North Pole, other time it is going under the area of South Pole. So in that way, because that flux, this means North Pole and South Pole, effect is getting changed. Consequently, the voltage will build up on the coils, and then you will be getting the DC voltage here. So therefore, everybody keep in mind, in case of the DC generator, armature will rotate. Armature means coil will rotate, but the magnetic field will remain static. That is the key point. But in case of synchronous generator, in case of real power plant, that the opposite is true. This means magnetic field will rotate and these coils will remain static. So you may ask the question why. So I will be answering at that time today when I will be discussing synchronous generator, and really at that time you will understand. At this point, everybody understand that to build up voltage, you must need two things. You need at least one set of coil and you need on magnet. Now in this case also, what you can do, like let me explain you. You can remove this on here. You can remove this on. What you can do, you can place the like north pole here and south pole here. You can attach it. So and then you can make another body here to which the north pole and south pole are mounted, and you just rotate the north pole and south pole, but don't move the coils. Still voltage will build up on the coils. But in case of DC generator, the all over the tradition is not to move the magnetic field, just move the coil. This means armature body. So everybody, could you follow me?
Yes, Dr. Ali.
Okay.
Yes, sir.
Yes. So just keep this thing in mind. Okay. Now go back to that slide. Okay. So I was in this slide. Now everybody see DC generator, armature, rotating part. This armature means on which coils are placed. DC field, stationary part. Oh, why it is called the DC field? This is basically that North Pole and South Pole, but that North Pole and South Pole always, they may not be magnetized. So you have to magnetize them with the application of DC voltage. That's why it is called the DC field. And then with the help of brass and commutator, that generated AC voltage is converted into DC. In fact, whether it is DC generator and AC generator, the first developed voltage is AC. Because the coil is moving and then the magnetic fields are fixed, or opposite can be true. So there is some change. That's why actual developed voltage inside the coil, that is AC. But then because we want to use it as a DC generator, that's why there is brass and commutator. So brass commutator arrangement kind of equivalent to rectifier, which can convert AC into DC. So that's why with the help of brass and commutator, that AC voltage is converted into DC voltage. And this is the required equation. You see in the equation, there is phi. Phi means that I have written down the meaning. Flux per pole. How many flux in Weber is originating or coming out from the North Pole and going into the South Pole. That is the meaning of phi. Capital Z is called total number of conductors. You see that I place the coil on that armature body. How many total number of conductors? If you put more conductors, then you will get more voltage. Okay, that N is called RPM, you see, the revolution per minute, the speed of that shaft. And then phi is called number of poles. This means that North Pole and South Pole. And A is called number of parallel paths. So you see in that whiteboard, I was showing you just one set of coil, but in real practice, there are several sets of coil which are placed in parallel. That's why it is called the number of parallel paths. How many parallel paths? So that you can produce more and more voltages. So this is just the governing equation. So therefore you can, for much more or further detailed information, you might refer to a electric machine book or any power system book. But just if you just keep this slide in your head, then that is enough to understand the dynamics.
Dr. Ali, I have a question.
Sure.
So the Z here is the total number of conductors, right?
Yes.
So this means like total number of coils as well, armature coils.
No, so let me then go back to that. Let me explain that. Okay, this is that whiteboard that we are discussing. You see, Can you see? For
Yeah.
example, this is on coil.
Yes, sir.
So so therefore, you see, this is on coil. In
Okay.
this coil, there are two conductors, kind of 50-50. You see, this one is on conductor, this one is the another conductor. So therefore, sorry, therefore this is on coil. So on coil means it has two conductor. So that is
Okay.
the definition of conductor and the coil. Do you understand?
So we are putting like a coil between two conductors generally.
No, these conductors constitute the coils. You see,
Okay.
for example, this is on conductor, this is another conductor. Next time we are twisting it in that way. We are twisting it. So therefore, in this case, you see how many total 6 conductor. This is one, this is one, this is number 3, this is number 4, this is number 5, this is number 6. So in this case, you understand? Yeah.
Yes,
Therefore,
yes.
so therefore, this is called one turn. So everybody remember on turn or on coil. So coil consists of two conductors, or one turn consists of two conductors. So therefore, this is on conductor. The remaining half is another conductor. That is the definition of conductor. So
Okay, I got it. Thank you.
yes. So therefore, you see, therefore I have twisted, twisted, twisted. This means there are many, many twisting. So there are many, many conductors. So this means, in other words, if I increase the, the twisting, if I continue, so the number of conductors are getting increased. This will essentially, the total length of the whole coil is getting increased. So that's why that will develop more voltage. Therefore, in other words, if you just put only like 2 or 3 conductor, maybe it will produce 10 voltage, but in that facet it will produce 100 voltage. If you put more coil, that will produce more voltage. That is the thing. So that's why, so we were there. Okay. So that's why that Z represents total number of conductors. So is this fine, Manoj, now?
Yes, Dr. Ali. Thank you.
Okay.
Sir, and what about like parallel paths? Could you please tell me?
Okay. So therefore, again, then let me go back there to that whiteboard. You see, so therefore, this is on-set of arrangement, just on-set. So the parallel means there can be another set of arrangement inside. Therefore, essentially, you see this armature body, I mean, because I am just drawing on circle, but it's like huge. I mean, in between there are lots of space. Therefore, first you place one set of coil arrangement and put another parallel set and put another parallel set. These are the number of parallel paths. How many
Okay.
sets of coil are placed? Like all are placed kind of, this is thing, this one and this one. These all are like the parallel connection, the similar meaning. How many parallel paths of coils or conductors? This is just the
So what would be the advantage of a parallel path? Like we can increase the voltage?
so the thing is that time to time these coils get damaged. So therefore, if you have only one set of coil, and then if that gone, then you are not getting anything. That's why there is alternative arrangement, parallel path. For example, if there are 3 sets, if this set is gone, then still you have the 2 more set. If this is gone, then still another set is present. And they are
Okay.
placed in parallel because, in case of parallel, voltage remain the same.
Yeah, yes.
Yes, you got it. So that's why in real practice, in real design, not just one set, the way I have drawn, there are multiple parallel paths.
So it's like a spare arrangement, right?
Yes, exactly.
Yes, sir. Thank you, sir.
Yeah, that is the like realistic consideration, placing the parallel things. Okay. Okay. So therefore, everybody will be just keeping in mind. And then the important thing is that which part is rotating. So I will be coming that synchronous generator. That time, again, like you will get fun. You just remember at this point that armature rotates, but that north pole, south pole, that remains fixed or stationary. And then you will be getting the answer why it is so here and why it is opposite there. You will be able to answer there. Yes. Okay, just hold on at this point. Okay, then I am moving that DC motor. So therefore, in case of the DC motor, you see already motor is like rotating. So I have taken the picture such a way. But you all know that the motor operation is that opposite to the generator operation. You know, in any case, like whether it is DC generator or AC or synchronous generator means it will produce voltage, and you have to provide mechanical input power. So mechanical input power means mechanical rotation. But in case of a motor means you need electrical input and then it will provide mechanical output. That is the basic difference between motor and generator. So therefore, for example, so you may have a ceiling fan at your home. So what is that? It is generator or motor?
Motor.
Motor. Why? Why is it motor?
Because we are giving electricity so that it's rotating it with the help of
Exactly,
the power.
exactly. So you turn on the switch, or you may have the string based turn on. So and this means you are injecting electrical power. So electrical power is the input, and what is your goal? You want to get air. So
Mechanical output.
exactly. So first it is producing mechanical output, and then you are getting the air from there. So that is the goal. So therefore, simply keep in mind, any motor means there will be shaft and that shaft will rotate. So therefore, that is latter, but first is the electrical input power. On the other hand, in case of generator means it will produce voltage. You will get power. But what you need the mechanical input power, which is that shaft rotation. So therefore, in case of generator, mechanical input power is the dominating factor. In case of the motor, electrical input is the dominating factor. Dominating means if you don't apply electrical input, you will not get rotation. So therefore, you see this picture, like I was explaining in case of generator, this is North Pole and South Pole. Clearly you can see. So North Pole, South Pole are placed. And this is that armature body. Just keep in mind, in case of motor, this armature, it will not rotate from the beginning. It is not rotating from the beginning. You see, once you have applied the DC voltage, you see plus minus sign, meaning that you are applying the DC voltage. Once you apply the DC voltage, only then it will rotate. But you remember, in case of DC generator, from the beginning, it is connected to mechanical system. I mean the prime mover, nuclear turbine or gas turbine or steam turbine or hydraulic turbine, whatever it is. From the beginning, there is mechanical power available. In this case, from the beginning, shaft is not rotating. Like think about your ceiling fan. Is it rotating from the beginning? No. Once you turn on the switch, only then, only once it overcomes its inertia, then it starts moving at its full speed. Do you understand what I'm telling?
Yes, sir.
Yeah. So, and then how it moves, everybody see, initially it does not move. Initially it does not move. This is like static, this shaft. Once you apply the voltage to the coils, those coils build up some sort of voltage, and that voltage causes some sort of flux. And already there is North Pole, South Pole placed. So then this North Pole, South Pole, they are also emitting the flux. So the flux is coming from North Pole and entering into South Pole, and again inside it is going North Pole, coming out. So there is on main flux here, but once you apply the DC voltage on these coils, then they will cause voltage and they will cause another set of flux. And this main flux and that flux will cause interaction. And because of the interaction, torque will be created and that torque will cause the rotation. So this means unless there is interaction, so this means that just the magnetic field is not enough or just the coil is not enough. You need the combination of the coil and the magnetic field. Do you understand?
Yes, sir.
Yeah. And then here there is one term everybody see. It is called the back electromotive force or the back voltage EB. So IA is that armature current. How much current is, once you are applying voltage, then current is entering into this body. So how much current is entering here? So that is that IA. And what is the equation? So RA is the resistance, armature resistance, the coil resistance. VT is the terminal voltage. How much voltage you applied here, which is VT. What is that EB? That is the back voltage. What is that EB? Once you apply the voltage, that VT, on these coils, before, so, and this EB is before the motor getting started. Initially, as I told you, it is not moving in that way. Just you applied the voltage on the coils, and that coils will create some voltage. That voltage is EB. So do you understand? Yeah. So therefore, everybody, you all will be just consulting a power system book or a machine book, that will be fine. So just you understand the operational mode or the working principle, then it will be fine. Okay, now I want to jump into the transformer. So now in case of transformer, so you all know the basic function, what the transformer does. So transformer basically, its function is to increase or decrease the voltage. For example, this is a transformer. It has two sets of coil, one on the left side. This body is called the magnetic core material. One thing, on set of coil is placed on the left side, which is called the primary side. On the right side, there is another coil placed, this blue colored, that is called the secondary coil. And you see, they are not electrically connected. This coil has no connection with this coil, but they are mounted, they are placed on the same magnetic core material. You see, transformer core. This is called the core material. Now, what happens once you apply the voltage here? For example, you applied 100 volt, and then what is the application? What is the consequence of application of the voltage on any coil? What will happen? What it will produce?
Some
Flux.
fields.
Exactly, flux. Exactly right. So therefore, the consequence of applying voltage or the current to any coil, it will create flux. This flux, everybody see, this green colored flux. This means because this is the same magnetic material, coils are separated, but once you apply the voltage on the left side coil, then it is creating flux phi. Then it started moving throughout the core. And once you see this flux, the same flux that is linking the right side coil, then voltage will build up on the right side coil. So do you understand that transformer principle? I mean, pretty interesting. Two sets of coil, they are fully electrically separated, but they are magnetically coupled with the help of core material. And how it is linking? With the help of magnetic flux. And then the voltage will build up on the secondary side. Now you can control the voltage. As I told you, for example, you have 100 volt left side, you can make 1000 volt, 10,000 volt, 1 million volt on the right side. It just depends on how many conductors or how many turns coil you place on the secondary side. On the other hand, you might apply 100 volt on the left side, but you might produce only 10 volt. It just depends on the control, how many conductors or coils you place on the right side. And then what is the principle? Look this equation, Faraday's law of electromagnetic induction. I think everybody from the physics you have studied Faraday's law of electromagnetic induction. So look the left side, this is Vs and this is Ns. Ns is the number of turns on the left side. d phi by dt. You look, because this is the AC, you are applying the AC voltage here. Consequently, this flux is also the AC in nature. This is not DC. This means that because AC quantity is time varying, alternating in nature. So this flux is moving, but this is alternating in nature. That is representing by the d phi by dt. This means flux are changing with respect to time. So therefore, because flux is changing, but your this coil are static here, consequently voltage will build up here. And then similarly on the secondary coil, you see Vp equal to Np d phi by dt. This here is the d phi by dt, here is the d phi by dt. This means the flux is the same because this is the same magnetic core material. So flux amount is the same, but the secondary voltage is related to N phi, number of secondary turns. So and then you see here is that equivalent circuit of this one. Like you applied a voltage Vp here, current is flowing, which is Ip. This is the primary sets of coil. So these two symbol represents the core material, core. This means in between only there is air, there is nothing. And then this is the secondary coil, secondary voltage, secondary current. This symbol represents the load. This means if you connect any load, then the current will flow. So the current will flow. And how they are related? This is the relationship. Vp over Vs equal to Np over Ns equal to Is over Ip. So see the relationship. And how we get this one, especially the voltage and the number of turns. Just divide this equation by this, or divide this equation by this one. So d phi by dt cancel. So you are getting Vp over Vs is Np over Ns. But in case of the current, it is opposite because you multiply this one, cross multiplication, Vp Ip equal to Vs Is. This means, as I told you, that the function of the transformer is to increase or decrease the voltage, but how the voltage can be increased? So voltage can be increased provided that current will be decreased. You know, according to law of conservation of energy, energy can neither be created nor destroyed. It can just be converted from one form to another form, right? So everybody know the law of conservation of energy. So, but what I am telling, the transformer can increase voltage. So the question arises, how is it possible that it will, does this mean the energy will increase? No, energy will not increase. Energy will be the same. So that's why if the voltage increase, current decrease, or if the current increase, then voltage will decrease. Therefore, look the relationship and you the cross multiply. So you will get the answer. Vp Ip, this means primary side power equal to secondary side power. So therefore your energy is not changed. Energy is the same, but you can change the voltage level, which is important and which is needed. So that's why you see, I have written that transformer means AC to AC conversion with higher or lower voltage. Now, why I have written AC to AC conversion? Like just few minutes back, we are discussing DC motor and DC generator. So in case of generator, I said it converts mechanical power into electrical power. In case of motor, it converts electrical power into mechanical power. What does the transformer do? It converts electrical power to electrical power. Do you understand what I am telling? So there is no mechanical component here. Therefore, left side is electrical, right side is also electrical. Just increase or decrease voltage or current magnitude. But both sides are the electrical. It is not mechanical or other form of energy. That is the difference. But the transformer is also called electric machine. Like motor generator, of course, electric machine, but transformer is also electric machine, although it does not have any rotating part. And then easily everybody can guess, because a transformer does not have any rotating part, consequently, its efficiency is very high. You know, there is little losses inside the resistances, and because of this core material, it is called some core loss, hysteresis loss or magnetic loss. There is some loss, but the amount of loss is very small. That's why the efficiency of a transformer is typically more than 95%. 98, 99%. Like if you see any book, power system book, electric machine book, and if you see the numerical example, always transformer efficiency is high. But if you solve any problem of motor generator, never ever you will see the efficiency is more than 80% or 85%. Even the real practice much less, like 60%, 65%. Can you guess why? Because in case of the DC motor, DC generator, or AC motor, AC generator, there is rotational losses because there is a shaft. There is friction loss, windage loss, bearing loss, other loss. But in this case, only loss is in the coil, small resistance, and some flux leakage loss. So that's why transformer is the most efficient piece of electrical equipment. In electrical engineering, this is the number on efficient equipment. Just simply, taking that way. And you might be asked this question, for example, if you work in power industry or in the job interview, you might be asked this question, why is the transformer efficiency so high? So you will be answering, because transformer does not have any moving parts or rotating parts. It's a static device. It's electric machine. It just converts electrical energy to electrical energy, either higher or lower voltage or lower or higher current. Everybody, could you follow me?
Yes, sir.
Yes. Sindhuja and Lakshmi, can you follow me? Is it fine?
Yes,
Do you have any questions or anything?
no.
Okay. So therefore, as I told you, like I'll be uploading this video, so you'll be getting my voice, plus you will be looking this one, and then you will match, or if necessary, you Google something or look a book, and then it will be fine. I mean, why I am emphasizing these things? I mean, when we will be discussing that power system stability, we will be going in depth gradually. That time, these things will come into picture. That time I will tell you just, okay, this is transformer principle. That time you have to quickly catch up this principle. Then you will be understanding. Similarly, I'll be, okay, this is the DC motor principle. That's why this is happening. That time you have to quickly go there. Oh, this is the DC motor principle. That's why I am just recapping these things. Yeah, I believe everybody, you all have studied in your at least undergraduate level. Oh, and then on the difference, you see, before I discuss DC generator, DC motor, definitely those are the DC. So is transformer a DC device or this is AC device?
It should be AC, right?
Right, it should be AC and it must be AC. So the question is, then I will ask the question, what will happen if you apply the DC here? So
Nothing will be generated. There won't be any flux change.
The coils get burnt. Right?
yeah, so therefore if you apply the DC, so therefore there will be a flux, but as Manoj replied, that flux will not be changing. The flux will be constant. And if it is constant, then there will not be any voltage build up on the primary coil. Consequently, there will be no voltage on the secondary coil. So this means that you can't transmit or send the DC power to the other side. But like as Venkat was adding, what will happen, because just it is causing that some loss and it is creating flux, there could be some loss here because of that constant flux, and that will gradually cause some heating in the magnetic material. So at some point, if it is prolonged, then this core material might be damaged. That's why it is not suggested at all to apply the DC on a transformer. So everybody understand? Yeah.
So Dr. Ali, can we use transformer as a DC filter or something like that so that we can remove the DC?
A transformer sometimes can be used as a filter because what is the equivalent circuit of transformer? Look this one. What you can see? What is this one?
Coils, primary and secondary coils.
Yeah, just the coil. So what is the coil? Coil is nothing but the inductor.
Mm-hmm.
So therefore, what is the function of the inductor? The property of inductor, that across a inductor, current can't change instantaneously. That is the basic property of inductor. Like for example, what is the basic property of capacitor? Across a capacitor, voltage can't change instantaneously. And across a inductor, current cannot change instantaneously. Therefore, because current can't change instantaneously, I am answering to your question whether it can be used as a filter or not. Yeah. So therefore, because of this property, because transformer is nothing but a like just coil inductor, there is very small resistance that is negligible, mainly the inductor. So for example, you have some sort of oscillation in a circuit, and then you put a transformer in between, you might see here the profile looks much better. Those oscillation might go away because this works as a filter. So therefore, in that sense, yes, transformer can work as a filter. So, but then you please never ever try to apply the DC on a transformer. Therefore, in one hand, it will not do anything on the right side, secondary side. The second point is that coils may get heated up over the time. Okay. Oh, and then the transformer is a AC machine, AC device. Simply keep in mind. And you see, and that is the reason, and that is the philosophy or background of developing the AC over the DC. This is the reason. Because as I told you that you can transmit the DC power over a long distance. The first reason is that you cannot increase it. And why you need to increase the DC voltage? Because there will be some loss in between. As I was telling you that from power plant, your home could be 500 mile, 1000 mile. Now, if it is DC, you can transmit it. Then on the way, it will be fully dropped, and ultimately voltage will be negative. That's why, to overcome that limitation, this transformer, this device has been invented or the discovered, because it can change the voltage and this thing can be connected to the line. So this is the motivation to discover the AC. But of course, you know, AC has more losses than the DC, but you cannot do anything because you have to transmit power over the long distances. Okay, so moving forward, yes, so these are the new slide that I have added for you that was not available before. So, and I already uploaded these things because after transformer, you know, we will be discussing synchronous generator, synchronous motor, induction motor, all are the three-phase AC system. That's why first I thought, let me put few new slides and that will help you a lot. So here you see what I am discussing, three-phase AC power generation system. So what is the advantage of three-phase system over the single-phase system? You know that in most cases we are the customers and we have single-phase system at home. And where is the application of three-phase load? That is mainly the industry, like three-phase induction motor, three-phase synchronous motor. So, and then what is the motivation or advantage? Efficiency increase, economical, output power increase, voltage current level increase, but maintenance decrease. These 5 bullets point are the main motivation or main advantage of the three-phase AC system over single-phase system. Therefore, just you look this picture. So in this case, you see there is a magnet and this is the AC generator. So this magnet will move with the help of the shaft. It is not shown here. And then these are the three-phase coils like AA prime, BB prime, CC prime. AA prime means for the coil, this is on end, this is the other end. For B prime, B, this is on end, this is other end. Same thing for CC prime. So this is called three-phase system. And you see from C prime, from B prime, and from A prime, there has been 3 lines. It is called three-phase output. But then the other end of the coil, like A, B, and C, they all three have been connected at a common point which is you see at the bottom, neutral line. So you all know that you need the neutral in case of the AC, whether it is single phase or the three phase. Therefore, this 3 is the actual output terminal, but then this is the neutral. Basically, this is the example of Y connection or star connection system for a three-phase system. Now, how this diagram will help you understand these 5 bullet points, everybody say, for example, you have on magnet, you must need the magnet that we already discussed. But for example, you have one set of coil. You placed only one set of coil like A prime. Therefore, that is the example of single phase system. Of course, that will produce voltage. Then you can make argument, okay, not this picture, I will make another set of generator. I will use another armature, another set of coil, which is BB prime, and then I'll be using another magnet. Of course, that will produce voltage. There is no doubt. And then again, you can argue, no, I will use another set of coil, which is CC prime, and I will be putting another coil, another magnet. Of course, that will produce voltage. Now, your argument is fine. You are absolutely correct that if you have 3 sets of arrangement, then you will be able to develop voltage and 3 separate systems. But the question is, will that be economical? That will not be economical, because you have 3 separate arrangement this type. Then when you need the maintenance, you need 3 separate engineer or 3 separate operator. If there is any issue in this arrangement, because all 3 phases are placed here, so just one engineer or one operator is fine for the maintenance or overhauling. So that's why, in that sense, this arrangement, 3-phase system is economical, plus maintenance is decreased during the overhauling or maintenance. Now, how the efficiency increase? Because your input is the same, this body is rotating. This magnetic field is rotating with the help of the prime mover, whether it is nuclear, coal, gas, or hydraulic, whatever. And then if you just put one set of coil, then it will produce voltage, but then you are just not taking the advantage of its rotation. So why not placing another set? Why not placing another set? So because you need the movement or you need a magnet, take the advantage of only one set of magnet and then put several set of coil. In this case, 3 sets of coil. This means you are able to get more output by using the same input. In that sense, efficiency increase, because efficiency is output over input. So in that sense, efficiency increase. Economical, then if efficiency increase mean because you are getting 3 sets of output, so definitely output power level increase, voltage level increase, current level increase. So these all are the motivation or the main features of having the 3-phase system versus the single phase system. Everybody, do you understand?
Sir, can I get some information on Y and delta connection?
Yes, so soon I am coming. Maybe in 5 minutes I am coming. Yes.
Yes, sir. Thank you.
Okay. Yeah. So I felt what you need, and accordingly, like I added this slide here. I would
Yes, sir.
know that you would be asking me those questions, and consequently, I have added those slides here. Yeah. No, I know. I felt that, like as a professor, I felt that I need those things, and that's why I added. Just wait a minute, just 5 minutes.
So, Dr. Ali, I have another question on this figure. So, the number of parallel path or some that is A in that formula.
Mm-hmm.
So, in this figure, is it 3 or how can we define that in this figure?
So in this case, when I say like AA prime, this means this is on set of arrangement. So inside that AA prime, there are multiple parallel paths.
Oh, okay, I got it. Okay.
Oh, here A prime, B prime means the 3 sets of arrangement, 3 types of arrangement, which we are calling the 3-phase. But inside in arrangement, there are multiple parallel paths.
I got it now.
Okay.
Thank you.
Very good. So these are the like realistic picture. If you have a chance to visit any real power plant, so you will be seeing they are placing the coil in this fashion. Okay, so now moving forward. Now you know that three-phase power means this is the AC power and the sinusoidal voltage. So how does the voltage look like? So for example, although I have given the name phase on, phase 2, phase 3, but these are basically phase A, phase B, phase C, according to three-phase system. So therefore everybody see, for example, this is the 0 point, look the phase 1. It starts, it is going up, it is coming down, and then back. So this is called like on full cycle, 360 degree. But then look for red colored on phase B. It is, look the zero axis, I mean x-axis, it starts after 120 degree, then the phase A. And then it is going, it is going, it is coming, and then again it is in that way going on. For phase C, it starts again another 120 degree, then the phase 2. This means with respect to phase A, it is 240 degree. So it starts from here and it is going on, and it is going in that way. That's why if you see for phase C, at the beginning you can see here, and for phase 2, it looks like it is coming here. In fact, like it is in that way going on. This one is going on in that way. Now, how you express those on phase on, this means if I am writing the voltage expression, same way you can represent the current also. It is the same thing. So VAT, Vm cosine of omega t, volt. So this Vm, this is called the amplitude or magnitude. For example, just look the phase 1. If this is phase 1, so from that zero axis, from here to here, this amount is called the Vm. And because this is the sinusoidal, that's why the cosine of omega t. And omega is that angular velocity in radian per second. And omega equal to 2 pi f. So you all know that. Similarly, for phase B, you see, there is a phase difference 120. You see, now if you compare the peak to peak, this point is called peak of each waveform. Just compare peak to peak, 120 degree. This peak to this peak, 120 degree. So that's why for phase B, VBT, Vm cosine of omega t minus 120. And then for phase C or phase 3, another minus 120. So it should be minus 240, but then anti-clockwise, it is plus 120. So therefore, hold a moment. So let me show you that thing. Okay. Let me erase these things because this is already saved. Okay. What I'm trying to say, okay, so everybody see, this is VA, therefore it has that magnitude, that Vm, and then it has the phase angle 0 degree, and then you go clockwise. So this means this is 120 degree minus 120 degree. So this means this is your VB. So that's why in the expression, like you noticed, that magnitude is the same, and then angle odds minus 120. And then this one is the, so this is A phase, sorry. This is B phase, this is C phase. So here you go another 120 degree. So therefore you see, from here to here all the way, this one is minus 240 degree. So this means this is VC, then you should write VC is Vm voltage magnitude and then minus 240 degree. But typically what is done, because this looks 0, this is minus 120, this is minus 240. Instead of doing clockwise for C phase, go anti-clockwise. So anti-clockwise, how much is that on? This is plus 120 degree, right? So that's why you will see the VC expression instead of minus 240, it is typically written like VM and then plus 120 degree. So then why it is done? Just to make the similarity with this one. This means B phase is minus 120, C phase is like plus 120. So then it is easy to remember. A phase has 0 degree, B phase has minus 120, C phase has plus 120, or in other words, minus 120. Could you follow me, everybody?
Yes, Dr. Ali.
Yes, very good. So now you see why I am showing this one. Yes, now come back this one. It is written plus 120. Look the C phase. So therefore it should be actually minus 240. But as I told you, if you assume clockwise, then that will be minus 240. But we have gone the anti-clockwise so that we get anti-clockwise 120. So then it is easy to remember. You have minus 120, here plus 120. Now I am answering to, I am going to like Venkat's question. Like he was asking that why delta. Now I am coming that in detail. Now everybody see, the first of all, there are two things. One is called the balanced system or symmetrical system. Other thing is called unbalanced or unsymmetrical system. This means the three-phase AC system is two types: balanced or symmetrical, unbalanced or unsymmetrical. So what is the definition of symmetrical or balanced? The voltage or current magnitude of all three phases are equal, and three phases are displaced by 120. So that you clearly noticed, I was showing the diagram in whiteboard, that each phase are displaced and each phase has the same magnitude. Like you remember, I was showing VM. Or for example, look this example. In this case, 120 0 degree, 120 minus 120, 120 angle 120. Therefore, in this case, this 120, first 120 is the magnitude of voltage. I mean, don't be confused with the angle and the magnitude. Magnitude is 120, and then here angle is 0, here angle is minus 120, here angle is plus 120. So therefore, those angles are called the phase angle, and magnitude are the voltage magnitude. The same thing goes for the current. So therefore, for example, in this example, you see clearly all three phases have the same magnitude, 120, 120, 120. But now see the definition of unbalanced. Voltage or current magnitude of all are not equal, but three phases are displaced by 120. Now come back this example. For example, angle is fine, 0 degree minus 120 plus 120, but for example here 120, suddenly it got dropped 100. Again it got dropped, it is 90. Or somehow those got increased, like 140 volt here it is like 130 volt. Therefore, that will be unbalanced system. And just keep in mind, unbalanced system is not desired. That is detrimental. That is harmful. So what is the problem of the unsymmetrical system? Just one example. Everybody see. For example, this is A phase and this is B phase. Now here, for example, 120 volt and here is 100 volt, for example, because unbalanced. What will happen? Some current will flow from higher voltage to lower voltage. Or for example, here 120 but here 90. Some current will flow from B phase to C phase internally, which is called the circulating current. And what is the consequence of current flowing? I square R, there will be some loss. And what is the effect of the loss? Loss means there may be some heating. System will be less efficient. And then what might happen? For example, you are a personnel, you are standing between phase A and phase B. You are standing between these two systems. One has 120 volt, other has 100 volt. Current will start flowing. If you are barefooted, you might get shock. Do you understand?
Yes, Dr. Ali, I have a question.
Yes.
So is there any chances like there would be like unequal phase displacement less than 120 or?
Yes, there could be. There could be, for example, you have a three-phase system And at the beginning of the installation, all three phases have equal impedance. They have all equal inductance and equal resistance. But over the time, for example, one phase has much more impurity, some corrosion or some sort of dirty thing added, and that changed its resistance. Or coil got little bit damaged. That set of coil will have different impedance than the other two. That time,
Mm.
phase angle might be different. And
Mm.
that is also the example of unbalance. So the good question.
Okay.
So this means that not only the voltage magnitude, if you see that phase angle has been changed, meaning that they are not properly maintaining the balanced. That is also the unbalanced. Got it? Yes.
Yeah, thank you, Doctor.
Yes. Okay. So and then still Venkat, still I did not go to that. I think Y and delta system. I am going to that. So
Yes,
before
sir. Yes.
yeah. So okay. Before slide number 9, let me go back slide number 10 and then okay, now Venkat, this is actually what you are looking for.
Yes, sir.
Everybody say that that whether it is balanced or unbalanced system, the coils can be designed, coil can be constructed in two ways. One is called the Y connection, other one is called the delta connection. So for example here, see, this is one phase, this is other phase, this is other phase. This is the three-phase system. But look here, all three sets of coil has one common point, which is this point. But look this arrangement. This is one set, this is second set, this is third set. You see, this set, they have a common point here, but the other two ends are not connected to the other end is connected with another coil. This coil, other end is connected other coil. And this looks like that Greek symbol delta. Accordingly, it is called delta connection. And you see, this looks like the symbol Y. If you see this one and this one, this one, accordingly it is called Y. Or if you say, okay, I am drawing a Easter, it looks like this three makes a Easter. That's why it is called the Easter connection. Now, what is the, I mean, advantage or relative disadvantage of each other? So just let's have a look. Now, everybody see, it has a common point, this point. So in this point, you can connect a neutral line. So therefore, this is three-phase system, A phase, B phase, C phase. But at the common point, you can connect a neutral line, which you need to finally connect to the grounding system for safety purpose. On the other hand, in the delta system, there is no provision to connect any neutral line. Can you see any common point among all three coils?
No.
No. So I mean, between these two, there is a common, these two, but then you are not getting a common point that connects all three coils. So this means that, keep in mind, the delta connection never ever has any neutral point, but Y connection, it can have the neutral, and that is the in real practice. So you all know that, So therefore, think about that like when you are driving long way, you are going somewhere long distance, you are driving, for example, Chicago, or you are going Nashville. Along the line, you might have seen 8 lines, eight cables. Therefore, those are the Y connection. This is on, this is on, this is on, neutral on. So then number 4, and another set, another, that redundant set or extra set, just for the reliability purpose. In case this set get damaged, then the other set will work. That's why always in real practice, over the long distance, double transmission line are provided in case one set get damaged due to storm or some other factor or maintenance. So that's why three-phase system, 3 coils, 3 lines, and then neutral on line, total 4 line, and then another 4 line additional for backup purpose, total 8 line you might see. Now the question is, then what is the necessity of the delta? So clearly you understand that because it can have the neutral, so then you can use on phase and neutral. That is, typical practice in our home, or in case of industry, 3 line or neutral. That is typical practice. But there is no neutral here. So how to use this one? Can you use this system at your home? No. because it does not have a neutral line. So then the question is, where you will use this one? What is the most?
In the motor and generator connections, we use the delta connection.
Yes. So, and then, no, you answered somewhat, but typically, you know that along the line, you remember that in last class I was explaining you the power flow from power plant to our home. There are some places from where you cannot use power. There are some specific location or the zone. There is no provision to take power. So because people cannot use power in those specific zone, so then use the delta connection. Why you will be using delta connection? You are saving the cost of the neutral line. You understand? Because this system, Y connection, there can be neutral, but neutral line is also a line. It's a cable. So it costs something. Whatever, yeah, you have to spend some money to get the neutral line. Versus,
Excuse me, sir.
yes.
Sir, but in case of Y connection, like most of the power system uses the Y connection, right? Because
Yes.
a factor of safety.
Yes, because of the safety. So that's why I'm telling that you need this one. I mean, this one is preferred, but this one is like you need another coil, which is the neutral line, yes, for the safety purpose. That's why for the use,
Yes.
for the people use, you must need the Y connection. On the other hand, the delta connection, it is saving the cost of neutral because you cannot connect neutral. But then where to use? Therefore, that thing I am telling that you are transmitting power over long distances. You don't need to use power because of high voltage. In that place, you can use the delta connection. Therefore, it is not always delta throughout the power network, but in some portion where you will not be, I mean, there is some rules, regulation, and standard as determined by the power operator. Okay, this 100 mile, there will be only delta connection just to save the cost of the fourth line. We will not be placing the Y connection because it needs the neutral. Place the instead of the Y connection, place the delta connection. Just transmit the three-phase power because we don't need to use the power for that 100 miles or 200 miles. But then again, when you need to use the power, convert from delta to Y because you need the neutral connection for the safety purpose. So therefore, like Venkat, that you are telling, in the power plant itself, it is the Y connection. And then immediately after that, there is a transformer. After transformer, typically the delta connection is used. But then again, once it is the distribution portion, most of the distribution line are again the Y connected because people need to use because it requires the neutral because you cannot connect neutral here. It is saving some cost because it is eliminating the need of the fourth coil, but fourth coil is needed, fourth conductor is needed for safety purpose. So do you understand everybody what I am telling? Relative pros and cons and the necessity.
Yes, sir.
So, Dr. Ali, I have a question.
Sure.
So, is there any, I mean, out of these two configuration,
Yes.
so does any of this one is preferred for unbalanced condition?
No, the unbalance may happen in either cases. Unbalance may happen in either cases, but there is, in case of the unbalance, for example, everybody see there is a neutral line here. For example, there is a neutral line here. So if there is any unbalance happen, the other thing is then probably you know that neutral does not carry actually any current. That is for the safety purpose, right? Yes.
Mm-hmm.
Now, if any unbalanced happen, I am answering to your question. If any unbalanced happen, this means that as I told you, there will be some circulating current flow.
Mm-hmm.
That time that additional current will start flowing through the neutral line.
Mm-hmm.
And then it depends on the magnitude. Like neutral is typically designed to maintain a certain amount of current. You cannot overload it. The neutral will be disconnected because it will be burnt out. But during the unbalanced situation, in this configuration, additional current start flowing through the neutral. And then you see the consequence, As I told you, if the magnitude is too high, let's say the neutral conductor were designed to flow 50 ampere, but 60 ampere is flowing, that might be disconnected. That because of it might be burning. And then this neutral connection, this here the common neutral connection of the telecommunication system in real practice, which is called the power line communication.
Mhm.
So therefore, in case there is any unbalance in this Y system, as I told you, that current will start flowing through the neutral, and that neutral current will again start flowing through the neutral line of the telecommunication line. Therefore, there are many examples that the telecommunication line got some interference or some issue. So therefore, telecommunication might be affected. So it has negative impact. Now, but at least you got a path that when it is unbalanced, there is a path to flow, which is the neutral path, and then it is grounded. And then even though the neutral line can be grounded, but for example, you are somewhere barefooted and you are working somewhat nearby that grounding place, and you are not aware of any unbalanced in this case. So what will happen? You suddenly got the shock, and you don't know that from where that current is coming, assuming that is soil or the land and it was wet or it's a rainy day and you were barefooted nearby the grounding. Do you understand?
Yes, Dr. Ali.
Because current was,
So Y connection is mostly preferred in the sending and receiving end, right?
yes, exactly. So in the power plant and then sending and receiving end, Y connection because of the safety. Now come back Manoj here and everybody. For example, there is unbalance in this case. So, and as I told you, the impact of unbalance, that there will be additional current, circulating current, and that will flow between phases. So in this case, where the additional current will go, because there is no neutral path. So what happens in real practice, those additional current start flowing through these coils, but they are blocked, because there is no neutral path. Here there is a neutral path, so it went until the ground. Here there is no neutral path, so they just get trapped, they just get blocked. And what is the consequence of that? Gradually these coils will be heated up, at some point might be burnt. So therefore, in this case, the possibility is that of the unbalance, this coil itself might be burnt out, system fully might be damaged. In this case, these coils typically does not burnt out. There are examples that these neutral lines time to time get overheated or the overloaded because of those additional current and got disconnected. And if it disconnected, then immediately you can fix. But in this case, because
So,
yes.
so how we are going to mitigate these issues in delta connection?
Okay, no. So you have to put some control means. For example, there is some sophisticated controller. It will detect that there is any unbalanced or not. Once there is any unbalanced, immediately there should be some sort of fault current limiter along the line.
Yeah, yes.
Yes. So therefore, Manoj, you remember you were telling about that inductor. There are some arrangement to prevent such situation. If you put any inductor here, that inductor will absorb some of those additional current,
Right.
and that will work as a filter. That will help somewhat. So
Mhm.
there are
So,
sophisticated means.
so like in a substation, we use reactors, the same thing there?
Yes, exactly that reactor.
Yeah, current limiting reactors,
Yes,
right?
yes. It is called FCL, fault current limiter reactor.
Yes, sir. Thank you.
And in case of the Y connection, there are some sophisticated method. Like for example, neutral line, and then in parallel there is on that type of fault current limiter. When it is overloaded, then use the parallel path. So just to divert some of the current, so that like frequently neutral line does not get disconnected because of the overburning or overloading. So do you understand? Yes.
Yes, sir.
Okay. Very good. So now everybody come back on important conclusion. Can you see, like Manoj, see this one? Now you answer me. For example, I have a voltmeter. Look the Y connection. I have a voltmeter and I connect a voltmeter between X and Y point. Oh, just one thing. These X, Y, and Z, these portions are called the line. So these things, the coil itself, these are called the phase coil or the phase portion. But once it is going here, it is called the line. But you see, in this Y connection, for example, some current was flowing, it is going. The current is the same. Although I am calling this is the line current, but the current is the same. Here current is the same, but this is line. So therefore, in case of Y connection, everybody remember the line current and the phase current is the same.
Same. Yeah.
But now everybody see, you connect a voltmeter between point X and Y. And then, for example, you got 100 volt. Just take an example. Now you connect a voltmeter between A prime point and Y point. Will it reading be the same?
Nope.
No.
It should be divided by √3, right?
Exactly. It should be divided by √3. I mean, at least the answer is it will be different, right? Yes, it is not same. Now come back, everybody, come back this side. For example, you have a ammeter. You connect the same thing. In this case, these coils, these are called the phase current or phase voltage. But X and YG, these portions are called the line. So now you connect a voltmeter, for example, here between X and Y. So therefore, for example, you got 100 volt. Now you connect another voltmeter here between C and C prime. What should be the reading now?
Same.
Same, because this point is essentially the same point. So this means in this case, voltage is the same. In case of the delta connection, the line voltage and phase voltage. But now you see, for example, you connect a ammeter here. Then you got 10 ampere, just an example. Now you connect a ammeter in this line. Will it be the same?
No.
No, it will be different because you see the current here 10, but you don't know how much coming from here and how much is going from there. So you cannot tell how much, but at least you can guess because this current is the combination of this current and this current. And again, you cannot say is it half or not. You don't know. So that's why in this case, line current and phase current is not the same. So what is the relationship? This current will be √3 times of this current. This means in this case, line current is √3 times of the phase current. But voltage is the same. In this case, current is the same, line current, phase current, but line voltage is √3 times of the phase voltage. Therefore, here is that thing I have written, what is called the phase current, when it is called the line current or something. Sometimes the line to line voltage, simply it is called just the line voltage. Just keep in mind, frequently in literature, line voltage means line to line voltage. Simply it is called line voltage. So now see this one, that example I was telling, everybody's left side is three-phase Y connection. This is on coil, this is other coil, this is other coil, and this is that neutral line. Therefore, see the arrangement. When I am measuring the voltage between the neutral line and any phase, I am getting 120 volt. Neutral and the phase say 120. This one and this one 120. But everybody see, once I am measuring the voltage from here to here, or from here to here, or here to here, between any two lines, I am getting 208. And if you have calculator, you see, 200 is √3 times of the 120. So, could you follow me? Now look this on right
It's
side.
between two phases, right?
Sorry? What you
Phase
said?
voltage between two phases.
So, no, so what I am telling that line to line voltage is √3 times of the phase to neutral voltage or the phase voltage. So
Okay, yes.
So phase to neutral voltage simply called the phase voltage. And when it is between two phase or
So
between,
VL is equal to root 3 times of V phase.
yes. So line to line voltage is √3 time of the phase voltage. So therefore, if you multiply 120
Yes.
by √3, that will give you about 208 volt. On the other hand, on the right side, you see, this is three-phase delta. So because this is the phase and this is the line, always the voltage is the same. For example, 480. But in this case, current will be different. We are just discussing the voltage. Current will be different. Current will be √3 times of this current if you measure the current. So therefore, so in that way, I have written down that conclusion here, you see, for delta connection, the phase voltage and line voltage are identical or equal. This means V line to line equal to V phase. For Y connection, the phase currents and line currents are identical. This means I phase equal to IL. For the delta connection, the magnitude of the line current is √3 times the magnitude of the phase current. IL equal to √3 times of I phase. And for Y connection, the magnitude of the line to line voltage is √3 times the magnitude of the phase voltage. So this is the things that I have already told. So therefore you are getting a summary here. And each of you must remember these things to solve the numerical problem. So hopefully in next class, I will be solving one or two numerical problems. So then now I think I skipped this slide. This slide, again, it's a summary, and I would recommend everybody to keep this slide in your head to solve any numerical problem about three-phase system. And these things will help you a lot to understand this course. So as the days go, we will be using a lot of numerical problems, a lot of theory. If you can just remember this, that will help you a lot. So again, you know that first two are just the recap, what we already told. For delta connected system, line voltage VL equal to phase voltage VP, line current IL equal to √3 times of the phase current IP. Okay, it was a little bit small. Okay, I think now you can see better. For Y connected system, line current IL equal to phase current, line voltage VL equal to √3 times of phase voltage. Now here, total three-phase real power. So phi equal to 3 Vp Ip cosine of theta. In this case, I am doing this one for the balance system. Keep in mind. So I am assuming that all three phases have same amount of power. So just I multiplied by 3. But if it is unbalanced system, you have to do it phase by phase. For example, Vp Ip cos theta for phase A plus Vp Ip cos theta for phase B plus Vp Ip cos theta for phase C. Because there is a chance of unequal value, so you can directly multiply by 3. Do you understand what I am telling? So therefore, this equation is for total three-phase real power for balanced system. For unbalanced system, you have to do phase by phase, one phase at a time. You cannot multiply by 3. But then here you see, I have used the term VP-IP to indicate phase voltage and phase current. But in real practice, voltage and current quantities are expressed in terms of line voltage and line current. For example, you purchase a three-phase motor and then you are looking the nameplate or its rating, and then you will be noticing it is mentioned, okay, line voltage 208 volt, line current is this, temperature is this, frequency is 60 Hz, etc. Always the voltage and current will be expressed in terms of line quantity, line to line quantity, not in terms of phase quantity. That's why in next two term, I am converting them into line quantity. See the symbol? Here it is 3 Vp Ip cos theta, but here √3 VLIL cosine theta. So keep in mind, it is not 3, it is √3. Then why that √3 is coming? Look the right side. This is my basic equation. P equal to 3 Vp Ip cos theta. As I told you, I want to change this VPIP into line quantity, VLIL. Now apply the above two rules, these two rules. In case of delta connection, what is the rule? VL should be VP. So I replaced this 3 is this 3, but I replaced VP by VL. What is the relationship of IP? Root 3 times of IP is IL. This means IP is IL over root 3. IL over root 3 cosine theta. So what I am getting? This root 3 cancelled, so then root 3 is here. That's why you are looking root 3. Same thing, and it does not matter, it is delta or Y system. And then do for the Y system, I did it here. Apply these rules. Again, you will be getting root 3 VLIL cos theta. So that's why I said this is valid for both delta and Y system. Same thing goes for the reactive power, Q root 3 VLIL sin theta. So you know the difference between real power and reactive power. So I mean, in a few seconds, I am showing you one diagram, and then we'll be concluding today. And then the apparent power is root over phi square plus q square, phi plus jq, root 3 VLIL. Because I am making root over phi square q square, so cos square theta plus sin square theta, you are getting 1. That's why this is. And then power factor, cos theta, real power over that apparent power. And you all know the unit of real power is what? Unit of reactive power is VAR, reactive voltage. Unit of apparent power is simply volt ampere. So everybody, can you remember this one?
Yes,
Yes,
yes, Dr. Ali.
Okay. And then just in like the 30 seconds, I will show you that power triangle, and then I'll be concluding today. I would recommend you, have you all looked all of the remaining slides like synchronous generator, synchronous motor? I think today we are almost done. So at the beginning of next class, I will be explaining the synchronous generator motor and induction generator and induction motor. Those are also very important to understand the stability codes. But today, let me just stop this on, and in a minute, once again on the whiteboard. Okay, let me erase this thing. Okay, so now see everybody. Okay, so this one is phi, this one is q, this one was that theta, this line is s, apparent power. Okay, and then this is called reactive power. So the unit is called watt. So here it is called real power. Unit is in watt, that you all know. This S is called, this is called apparent power. And unit is volt ampere. And this theta, this is
power factor.
the power factor. So this is cos theta.
Cos theta is power factor.
Yes.
Theta is just the power.
Yes, yes, exactly. This is power factor. And this power factor is, you see, that P over S. P over S. From this triangle, you know, this is cosine theta. So base over
Active power by apparent power.
Yes, yes, exactly. So therefore, everybody, please you try to remember this one. You need this diagram in your head in addition to those equations. That will help you a lot to solve many problems. Okay, so I'm saving this one also, so you can see. Okay, so therefore, everybody said that this one is that that slide that I was showing you at the last time. I think this slide. Yeah. This is the summary, that diagram. That is called the power triangle. Power triangle. Okay, so with that, I like to conclude here today. You keep going, and then at the beginning of next class, I will be covering a little bit, and then I will be covering the new things. Do you have any question, comments?
So Dr. Ali, can you hear me?
Sure, yes.
So the APRI is conducting some kind of a tutorial for OpenDSS and OpenDSS-G from August 24 to 27. It is free. If anybody is interested, I can share the link.
Okay. Yeah, and so you can send an email to everybody. You can send an email.
Hello?
Hello, yeah. So I said that you can send an email to each of us. So you can send that information.
Can I share it here or?
Oh, you want to show it here that you are telling?
No, I can give the link and they can, if they are interested.
Yeah. So that's it. Please email to us.
Sure, Dr. Ali, I'll email it.
Yeah, you have everybody's email, right? Because I sent some class.
Yes, Dr. Ali. Yes,
yeah, please email us. Yeah.
Sure.
Okay, so is there any other questions, comments from anybody?
No, sir.
Okay.